And then other work shows us that quantum entanglement connecting two particles is just like a wormhole, going from one to the other.
Because what happens in one happens to the other instantly.
Yes.
And that means they're touching each other in that instant.
Connected in some weird way. And entanglement is one language, but we believe wormholes may be the general relativistic version of that quantum language.
So it's like a little quantum net holding the whole universe together.
Exactly right. Because we find mathematically, if we cut the threads of quantum entanglement, which we can do mathematically, space falls apart.
So why does the universe seem to measure distance not with meters and miles, but with how tightly things are bound by quantum information? We grow up trusting space. You can step it off, mark it with a ruler, map it with grid lines. But when two quantum objects are prepared together and carried apart, they can behave as a single, shared system no matter how far the separation. Experiments have violated Bell's inequalities over and over. The outcomes are correlated beyond any classical script. Yet no usable message zips between them. Nothing outruns light. That's the first jolt to intuition. Nature forbids faster-than-light signals, yet still yields correlations no locally causal story can reproduce. If our measurements of place are so reliable, why do the deepest laws behave as if proximity is not about locations, but about relationships? Einstein taught us that matter tells space how to curve, and curved space tells matter how to move. But an unexpected development in theoretical physics suggests a reversal. Patterns of quantum correlation may tell space whether to exist between things at all. In certain universes, we can actually calculate with confidence, those that behave like a hologram, the amount of quantum entanglement in one region is encoded in the area of a surface in a higher dimensional geometry. Entropy on the boundary, area in the bulk. It's an equation that lets geometry and information talk to each other in the same breath. The more two regions are entangled, the closer they are in the emergent space. Within those models, stronger correlations track tighter geometric links, reduce that correlation, and the effective separation grows in the reconstruction. Build a network of many small entanglements and a smooth landscape appears. Cut away enough links and the landscape fractures. In these models, that's not just poetry. It's a ledger. Area is bookkeeping for how much quantum stuff is shared across a divide. If space can be inferred from correlation, perhaps our old question, what is distance, has been misspecified from the start. Now, consider the most dramatic arenas of gravity, black holes. Einstein and Rosen found solutions where two regions of space-time are joined by a tunnel. Meanwhile, Einstein, Podolsky, and Rosen, yes, the same initials, highlighted the mysteries of quantum entanglement. Decades later, a bold conjecture proposes that these two ideas rhyme. Certain entangled systems behave, in a dual geometric picture, like two mouths of a tunnel sewn together by the very entanglement that links their states. It is not a highway for violators of causality. The tunnel is sealed to prevent faster-than-light travel, in harmony with the no-signaling fact of entanglement. That tension is the point. Connectivity without communication. If you delicately couple the systems, quantum effects can inject a pulse of negative energy that briefly opens a door wide enough for a single bit to get through, then snap shut again. The equations show how. A few years ago, a modest quantum processor implemented a toy model where a signal, teleported with the help of entanglement, could be reinterpreted, mathematically, as a message crossing a tiny simulated tunnel. No starships were involved, just qubits and gates. Yet the moral lands hard, that the same logic that routes information in a circuit can appear, from another vantage, as the motion of something through space. Geography becomes a dialect of computation. This reframes an old cosmic riddle. What happens to information that falls into a black hole? If space and information are dance partners, they must keep in step. For decades, Hawking's calculation hinted that information evaporates irretrievably, a violation of quantum law. Recent progress redraws the plotline. When you properly account for quantum extremal surfaces, places where the trade-off between area and entropy balances, entropy of the radiation rises, then falls, matching the expectation that information ultimately returns. And the reconstruction program says something even stranger. What you think of as inside a region can be recovered from data outside, depending on how the entanglement is stitched. change who shares quantum correlations with whom, and you change which degrees of freedom count as interior. Somewhere can move. Not in the way your car moves, but in the logical sense of which systems contain which secrets. If awareness can be reassigned by reweaving relationships, then the noun place starts to look like a verb. That should make you wonder about us. You and I are arrangements of particles whose identities blur without the correlations that knit them into a body, a brain, a memory. We are open systems, radiating heat, exchanging photons, constantly entangling with the environment. Our experience of nearby and far away is not wrong. It's an emergent convenience. The world is organized so that the strongest correlations fall off with distance in the usual meter-stick sense. That's why locality works so well for daily life and for most physics. But if the bedrock is correlation, then near really means highly coordinated, and far means almost independent. The cosmic microwave background still hums with remnants of quantum fluctuations that inflation stretched across the universe, preserving phase relationships that seeded galaxies. The structure we inhabit is a fossil of early entanglement, amplified to astronomical scales. The stakes become personal. Maybe the boundary between self and world is not a wall, but a gradient in correlation strength. Follow that thread, and another puzzle emerges. Time. General relativity fuses it with space, yet time has an arrow while space does not. In certain models of quantum gravity, the interior of a wormhole grows with time, even when no matter falls in. That growth appears to track something called computational complexity, how difficult it is to reassemble a state from simple operations. Imagine a deck of cards perfectly ordered. Each shuffle scrambles correlations. To unscramble requires an ever longer sequence of precisely chosen moves. The universe is shuffling. As entanglement spreads and complexity deepens, the length of certain geometric features swells. The clock's arrow may be pointing toward increasing difficulty of reversing the cosmic computation. If distance is about correlation, then time might be about effort, the number of steps needed to unwind what the universe has already woven. None of this licenses science fiction shortcuts. You don't get to wink across the galaxy with an entangled friend, because correlations aren't commands. They're agreements nature made in advance. You don't casually open a tunnel between stars. Geometry resists, demanding exotic energy and exquisite control. But the picture we're sketching resolves the opening question. Meters and miles are reliable because the universe chose a phase where correlation strength roughly tracks physical separation. Yet, in the deep architecture, relationships come first. The fabric we move through can be reconstructed from who shares information with whom, how much, and in what patterns. General relativity reads the bulk of that book. Quantum theory writes the sentences. Holography shows that the margins are filled with codes that protect meaning against noise. Distance, in this light, need not be primitive. In those frameworks, aspects of it can be reconstructed from patterns of entanglement and correlation. So why does the universe seem to measure distance with relationships? Because in these frameworks, what we call space can be mapped from correlations, connectivity, entropy, and complexity relating quantum information to geometry. Remove the relationships, and the map loses its roads, enrich them, and paths appear where none were before. We live inside that map, navigating a world whose coordinates are, at bottom, agreements etched in the language of information. Like if this was interesting, and hit the subscribe for more.